There's a question here from Jimmy. Could we be inside a black hole? Can biological life survive inside a black hole? Well, so first of all, what is a black hole? A black hole is something where there's so much gravity that even light can't escape from that area. So what happens is when you have the Earth, for example, if you shoot a rocket up from the Earth, if you don't shoot it up fast enough, the gravity of the Earth will just pull it back and it will crash down on the Earth again. If you shoot it faster than 25,000 miles an hour up from the Earth, it will escape the gravity of the Earth. It goes fast enough, it has enough momentum that it can break away from the gravity of the Earth and just go off into space. Every different kind of object, depending on its mass and how big it is, will have a different escape velocity. So, for example, the sun has an escape velocity of maybe 100,000 miles an hour. Our galaxy has an escape velocity of, I think, about 1 million miles an hour, and so on. But what happens is if there's enough mass in a small enough volume, in a small enough sized object, the escape velocity eventually becomes higher than the speed of light. So that means, because it seems to be a fact about physics, there are some footnotes to this that come out of our new models of physics, but basically nothing gets to go faster than the speed of light. And so if you have something where the escape velocity is the speed of light or larger, that means that even light, even something which goes as fast as light, can't escape. So that means that there's this region of space where anything that tries to get out will be sort of pulled back in and can never escape. So in particular, in a black hole, there's this thing called the event horizon, which is this place in space where it turns out that any light that originates inside the event horizon will always get pulled back inside and will never escape. And everything outside the event horizon can escape. And it was very confusing to people when black holes were first kind of thought about. The equations that describe the structure of space-time, the equations of general relativity that were invented in 1915 by Albert Einstein, those equations kind of describe how mass and energy deform the structure of space-time. And that deformation of the structure of space-time is what leads to gravity. As soon as you kind of change the shape of space, you change kind of the ways that things go on shortest paths. By deforming how those shortest paths go, it's deflecting how sort of objects move through space, and that's kind of has the effect of is the thing that leads to the force of gravity. But in any case, the equations of general relativity implied that you could get these funny singularities, these funny sort of 1/0 type things going on. And people were very confused. Actually, Robert Oppenheimer was one of the people involved with this in the 1930s, early 1940s, trying to sort of unravel what was really going on in these cases where there were these kind of 1/0 infinity type singularities in the sort of structure implied for space-time. And people at first thought that when you have this event horizon, that if you were in a spacecraft that was kind of falling towards a black hole, and you went through the event horizon, people sort of thought, oh, something terrible is going to happen at the event horizon. Turns out that's not true. Turns out you wouldn't even notice going through the event horizon. The only thing that would happen is that the signals you send out, you wouldn't know, you'd be waiting forever and ever for, as you get close to the event horizon, a signal you send out is kind of pulled back a bit. So it takes longer to get out than you might expect. But eventually you might send some signal out to some other spacecraft or planet or whatever, and eventually somebody might reply and you get the signal back. What happens as you go inside the event horizon is that the time for your signal to reach its destination becomes infinite. You'd never get an answer back. Your signal would never be able to reach the sort of the sender. But you wouldn't notice as you go through the event horizon, you wouldn't really notice anything bad happened. It would only be if you waited for signals to come that you'd sent out to come back. They wouldn't ever come back. So this question was, what's it like to be inside a black hole? Well, as you pass through the event horizon, nothing much happens. It's only kind of in the long view of history that you would realize you were now kind of nothing you said could ever be heard outside, so to speak. But then, as you sort of you're sort of falling into this black hole. Now, there's a bit of an embarrassing feature about black holes, which is the mathematical theory that describes black holes kind of tells you how event horizons work and things like that. They don't really tell you much about what happens inside the event horizon. In fact, as far as the mathematics is concerned, it doesn't really matter if there's anything inside the event horizon. Well, pretty much anything inside the event horizon. In reality, a black hole is formed when a massive star collapses and is pulled by the force of its own gravity into this tiny area. And that produces enough kind of mass and a small enough volume that you get larger than speed of light escape velocity, and you get a black hole. But so inside the event horizon of a black hole, you would normally, you would think in physically that what would happen is the way it will be formed is that there's a collapsed star and there's all kinds of stuff from the collapsed star inside the event horizon. But because you can't find out what's happening inside the event horizon from outside the event horizon, because no information about what's inside can get out, you don't really know there's a collapsed star inside. You might know from the past that, oh yeah, we saw the star, it was collapsing now that must be what's inside this event horizon, but you can't know that from just seeing the event horizon of the black hole. So that's sort of so in the mathematics of what goes on, the structure of the event horizon and all those kinds of things is quite independent of what's inside. It could be this, there could be this whole civilization that's going on inside. They could have a whole, it could be this thing that's this shape, it's that shape. It doesn't matter. Outside, it all just looks like this kind of sphere of event horizon. Well, it's even more bizarre than that, because in the usual mathematical theory, there can just be vacuum inside the event horizon, with one exception. There has to be some kind of puncture in the structure of space-time. There has to be a single point at which the structure of space-time is changed, a single point at which, for example, the curvature of space-time becomes infinite. Now, in our models of space-time, things are not nearly as pathological as that. In our models, there's this kind of network that represents the structure of space, and space is ultimately composed of these just individual points related by the edges in this network. And so when we say that what happens when you make an event horizon, for example, is certain features of that network, or actually the certain features of the way that network progresses through time, work in a certain way. And what happens at the center of the black hole, where you have this singularity in space-time, in sort of the traditional view of space as a continuous thing, the only way you can deal with that is to say there's a hole punched out of space-time, where there just is no space-time there. It's just an infinitesimally small hole, but there's a hole. So in our models, it doesn't quite work that way. You can have something much more structured. You can actually see the structure of the network is different as you get in towards the singularity at the center of the black hole. But one feature of that singularity is, for the simplest kind of black hole at least, is that time stops. So in our model of physics, what's happening, time is this sort of progressive computation of the state of the universe, the next state of the universe, the next state of the universe, always being computed from the previous state. And in sort of structurally, what's happening is you have this giant graph, and at every step, all the different pieces of this graph are being rewritten. And so sort of the progress of time is the progressive rewriting of this graph. And everything in the universe is a feature of this graph. Every electron, every whatever, they're all just features of the structure of this graph. And so time is this progression of sort of the rewriting of this graph. Okay, so what happens at these singularities? In the simplest kind of black hole, non-rotating black hole, in the simplest kind of black hole, what happens is time just stops. So what does that mean? It means that at the center of the black hole, there are pieces of the network where no more rewrites apply. There isn't another rewrite that gets done. It just stops. So it's it's if you were sort of part of that, it's kind of like your mind just stops running, your brain stops running. You won't. It's not like, oh, I'm realizing I just froze. You don't realize anything. There's no thinking going on. There's no mind. There's no experience happening. Time just stops. And in the so what happens in the sort of traditional view of things is the spacecraft that fell through the event horizon eventually is led into that singularity at the center of the black hole, at which point time stops. And it always, after a limited time, the spacecraft always ends up at that singular point at the center of the black hole. In our models, it's a bit more explicit what happens, but the end result is at some moment, the time is frozen. Nothing ever happens anymore. So you don't know what happened because time is frozen for you as it's frozen for everything else. So in this question of can you sort of lead a happy life inside a black hole? Well, up to a point, eventually you die, so to speak. Eventually there's no more experience that happens. That's the case with the simplest kind of black hole. With the other kind of black hole, you get a more bizarre thing still. In rotating black holes that effectively are rotating, you get, so the thing I just described is called the space-like singularity. There's another kind of singularity called the time-like singularity, where instead of time stopping, effectively space has stopped. What does that mean? It means that normally in space you can move back and forth, you can move around, there's extent to space. But in a time-like singularity, there is no extent to space. Space is infinitesimally small, and you are sort of trapped in this infinitesimally small region of space where all that can ever happen is the same thing keeps on happening over and over again through time. And that's kind of a different, so there time is infinite, but space is infinitely small. So that's a different kind of singularity that can happen. But in both of these cases, it's kind of not like you notice anything really bad happened, because you don't get to notice anything because your mind is kind of frozen at that point. So, but in terms of can there be a sort of if you after a limited time, everything comes to an end. Now, for our universe, could be the same thing. It could be that in our universe, we expand for a while, and then gravity pulls back the expansion of the universe, and eventually it goes crunch in a big crunch. That doesn't seem to be the path that our universe is on, based on the speed at which the universe is expanding and other kinds of things we can measure. It seems like we're just going to get to the point where we're just eventually coasting and going, and we're not going to we're neither going to speed up in our expansion, nor are we going to sort of turn around and crush down again. But if we did, it can still be the case in both scenarios that sort of you can end up with a situation where, again, for the whole universe, time eventually ends, and where sort of we keep going for a long time, and then eventually it's all over and time has ended. The possibility where the universe just sort of expands forever at an increasing rate, you can get into a situation where it expands forever, but the rate increases, and eventually everything gets so far apart that, at least in the traditional model, so far apart that kind of nothing very interesting can happen anymore. I actually, now that I think about it, in our models, it would not really work that way. It would not be the case. That would be an approximation. And if you look below that approximation and you look at the actual structure of space-time, there will still be features of the actual structure of space-time. It won't be the case that the thing has become sort of uniform and boring. And in fact, in our models, again, even with the sort of the big crunch scenario, again, it won't get the same way as it does in kind of the older models of physics, where the thing just sort of compresses to a point and there's nothing more going on there. It's a little bit more structured than that. So that's a little bit of a discussion about, could we be, what's inside a black hole? Can things survive in a black hole? The answer is yes, but only for finite time, typically. But we are, our universe may only survive for finite time as well. And there's an awful lot of time before let's say our universe survives for 1 trillion years. We're about 14 billion years in, and we can lead happy lives for an awfully long time, even if the actual lifetime of the universe is, quotes, only 1 trillion years. So we're kind of existing in what one can think of as kind of we might think we're existing in sort of the transient before the real outcome of the universe is known. I don't think in our models, for example, this idea that things become very different when the universe is either crunched down or gets very big or whatever else, it's a little bit of a subtle thing, because what it means to an observer like us today, we're roughly 1 meter tall, give or take 1.5 meters tall, whatever it is. And to an observer like us, if we imagine what the universe might be like when it's crunched down or it's really big or whatever, we say, oh, that doesn't look very interesting. That looks like nothing that we can kind of engage with. But that's because we're 1.5 meters tall or whatever, and we have certain things we can measure. If we imagine sort of projecting the future of humans, not really humans, very likely, 1 trillion years from now, and we say, well, what do we sense then? Well, we're probably not 1.5 meters tall and made up with, biological molecules and things like this. And with a different kind of observer, the structure of the universe as it might exist at that time in the distant future can be perfectly exciting and interesting, even though to an observer like us, it isn't interesting. So it's and the same is true of a lot of these different kinds of things. The question of is there kind of what's one's impression of what's going on? Well, it depends on what one is like as an observer.